Now, the purpose of a augmented matrix, though, is to actually condense the form of elimination that you learn how to solve with when you did a linear system. And so we're actually shorthanding that form right here. And here's what it says. We've been given three unknowns, three linear unknowns, x1, x2, and x3. And again, we can write these above these values like this. Here is x1, here is x2, and here is x3. And from this, I should be able to solve this by using a process that we call back substitution. Back substitution. And all back substitution is, once you get a variable, you can go back and substitute it in for other variables to find the equations. And there are three types of equations, or three types of matrices and systems that you can solve. The first one is called a consistent and independent system. In a consistent system, you always get a solution. If it's independent, the solution is unique. Unique just means you have a different value. You have a set point that you're going to get. So here, if we write out the equation, it looks like this. We have first equation would be x1 plus x2 plus x1 plus x2 is equal to 4. Next equation says x2 plus x3 equals 2. And then the last one says that x3 is equal to 3. Well, when I look at this, then we call it back substitution because in solving this equation, I see already that the x3 variable is equal to 3, which means now I can go back and find, by back substituting, I know that x2 plus, well, x3 is equal to 3. So that's 3. That has to equal 2. So I went back and I back substituted, or I substituted in for that variable there. Solving this equation for x2, I'm going to subtract off 3 on both sides. And I get x2 is equal to -1. Now, once I have that, I know what x3 is. I know x3 is 3 and x2 is -1. I can go back and find x1. x1 plus, well, x2 is -1, so that's x1 plus a -2 has to equal 4. Rewriting that, I get x1 minus 2 equals 4. Solving for x1, I'm going to add 2 to both sides. And I get x1 is equal to 6. So now I get this unique solution of x1 is 6, and we can write it as a point. x1 is 6, x2 is -1, and x3 is +3. This is called a consistent. It's consistent because we have a solution. It's consistent because we have a solution. And it's called independent because that solution is a unique point. It's called consistent and independent. So look at the next example. Again, we can write out the variables here. Here is x1, here is x2, and here is x3. So we write this out. We have x1 plus x2 plus 2x3 has to equal -1. Then we have x2 minus 4 times x3 has to equal +4. And then the final equation I have is x3 has to equal -1. So back substitution works now because this is already telling me what a variable is. And if I know a variable, I can go back and substitute wherever I have it, where I have a variable already sitting there. So here I know that x3 equals -1. So x2 minus 4 times x3, but x3 is -1. That equals 4. So I get x2 plus 4 here. That's a +4 equals 4. I'm going to subtract 4 from both sides now. And I get x2 equal to 0. So now I know x3 is -1, x2 is 0, the last thing I want to find is x1. So x1 plus, well, x2 here is 0. So that's 0 plus 2 times x3, but I know x3 is -1. That has to equal -1. So when I clean this up, I get x1 minus 2 equals -1. Solving for x1, I'm going to add 2 to both sides. And I get x1 equal to a +1. So now I can see that I have a unique solution of, as a point, 1, 0, -1. This means that this system itself is consistent. I get a solution. It's consistent and independent. It's a unique solution. This next type of system that we're going to talk about is what we call a consistent and dependent solution. So in a consistent and dependent system, it's consistent because you're going to get a solution, but it's dependent because your solution is actually dependent upon whatever value you give for the variable. And this happens because all 3 of your equations are the exact same equations. And when you do this, when you start this, you're always going to have one more number than you will variables. And you always see a row of zeros. So anytime you see a row of zeros in your system, like this right here, we have the row 0 at the bottom, this tells me that I'm going to need what's called a dummy variable. I'm going to need a dummy variable, and we call our dummy variable t. So what the first thing we're going to do is we're going to write this above this again. Here is x1, here is x2, and here is x3. So when I write my equations out, I get x1 plus x2 minus 3x3 has to equal 4. First equation. Second equation is negative x1 plus 5x3 is equal to a -6. And then there's a problem now because in order to solve any kind of system, however many unknowns we have, in this case we have 3 unknowns, we need that many number of equations. Well, the problem is we only have 2 equations. So to make this work, what we always do is we're going to set that last variable x3 equal to a dummy variable, which we'll call t. So x3, the last variable, will always be equal to the dummy variable t. And in this case, what we're going to do now is we're going to write every other equation in terms of t. And so that means we're going to go back and plug in for x3, that t variable. I'm sorry, this should have been an x2. So when we write this out, we get this negative x2 plus 5 times x3, but x3 we're calling it t. That has to equal -6, right? And so now I get negative x2 plus 5t equal to a -6. I want to solve this equation for x2. So the first thing I'm going to do is I'm going to move the 5t over by subtracting it from both sides. When I do that, I get negative x2 is equal to -6 minus 5t. The next thing I'm going to do is I'm going to make that x2 be positive. So I'm going to divide everything by -1. That just flips all the signs. So here's what I get for x2. I get x2 is equal to 6 plus 5t. Notice how x2 is now written in terms of t. So using the dummy variable, I have x3 written in terms of t. I have x2 written in terms of t. I'm going to go back and write x1 in terms of t now. So now I have x1 plus x2. Using this equation right here, x1 plus x2. But x2 is equal to this right here. So I'm going to plug in 6 plus 5t for x2 minus 3 times x3. But again, remember, x3 is equal to just t. All of that has to equal 4. So when I clean this up, I get x1 plus 6 plus 5t. I'm going to distribute out this right here. It'll be a negative 3t that equals 4. Cleaning this up by combining these like terms right here, I get x1 plus 6 plus 2t equals 4. I want to get x1 by itself, so I'm going to subtract 6 on both sides. I can subtract 6 from 4 right here. And I'm also going to move the 2t over by subtracting it, minus 2t. So when I do that, I get x1 is equal to a negative 2 minus 2t. Notice this, x1 is positive, so we're good there. And it's all written in terms of t. And so the way this works now is, when I state my solution, I'm going to write it as a point again. So I get one solution of, the first part, x1 is negative 2 minus 2t. The next part is 6 plus 5t. And then the last part is just t. And this is called a consistent system because we have a solution, but it's called dependent because it's dependent upon whatever the value of t is now. So I can give you any value for t. Let's say I say that t equals negative 1. Well, if t equals negative 1, then I'm going to get this here. Negative 2 minus 2 times negative 1. 6 plus 5 times negative 1. And then negative 1. Or in this case, that would be negative 2. Negative 2 times negative 1 is a positive 2. So it's negative 2 plus 2. That is negative 2 plus 2. That'll be 0. 6 plus a negative 5 is 1. And the back is negative 1. So when t is negative 2, negative 1, this is the solution I'm going to get. 0, 1, negative 1. If t is another value, for instance, let's say that t was equal to 0, then again, I would do this. Negative 2 minus 2 times 0 times 6 plus 5 times 0. And then t would be 0. So my solutions are going to be, well, this is just negative 2. This is 6. And this is 0. So notice how how the solutions are dependent upon what t is. And again, this occurs when we go into our system, when we start our actual system, we saw that we had a row of zeros. When you have a row of zeros, you have to go through this using this dummy variable process. This last type of system we're going to talk about is called a inconsistent system. In an inconsistent system, there are no solutions. And typically when you talk about an inconsistent or no solution system, it means that your lines are parallel. They never intersect. And realize this, that's what we're really talking about. Lines are intersecting in consistent solutions. In an inconsistent solution, they do not. So again, you have these variables here. You have x1, x2, and x3. And then notice when I come down here, though, I have a row of zeros, and it's equal to a number. Because you have a row of zeros that's equal to a number, already this tells me that this is a inconsistent solution. There's not enough variables. There's not enough variables to solve for this to begin with. And we can't write the dummy variable because we have this number saying that 0 equals 1. Literally what you're saying here is that 0 is equal to 1. It's a false statement. And because this statement is false, we call this no solution. So anytime you see a row of zeros equal to a number in an augmented matrix like this, the answer is no solution.